So in the previous problem or example, we looked at picking a bottle of chocolate milk from a population of bottles of chocolate milk, and we were picking a single bottle. In this example, we're actually going to pick a random sample of 8 bottles of chocolate milk. So this time, out of the entire population, we're going to choose 8 bottles from that large population, and we're going to find the mean of this random sample, and we're going to call it X bar. So let's look at the facts here. So the facts are that we have a normal distribution with mu equal to, or the mean equal to 1.0875, and the standard deviation equal to 0.015. So I can draw this on a graph. Here's my graph, and here is my normal distribution. And so now we're talking about a sample of 8 bottles rather than a single bottle that we're taking from the pack. So when we talk about that, we're actually talking about, instead of talking about the mean here, we're talking about the mean of the sample, of the random sample. So we're looking here at X bar. And we know that the mean is actually of a random sample that is normally distributed. We know that the mean is always equal to mu, or the population mean. So in this particular case, the mean here is going to be 1.0, or mu is going to be equal to 1.0875. And the standard deviation we need to calculate for this sample mean, but the standard deviation of the population we know is 0.015. So these are sort of our facts. This is the stuff that we know so far. And we also know that the sample size, the sample size, n, is equal to 8, because we know that we picked 8 bottles of chocolate milk from the pack. So our n is equal to 8, and we know mu in the population standard deviation. So now, how do we figure out, sorry about that, how do we figure out, So in the previous example, we looked at pulling a single bottle from a population of bottles of chocolate milk, and we determined what the probability was that bottle, that single bottle that we pulled, would actually exceed 1.1 pounds. In this example, we're looking at the mean of a sample of bottles of chocolate milk. In this particular case, we're looking at a sample size of 8 because we're choosing 8 bottles out of the population, and we're calculating the mean of those 8 bottles in pounds. So we can represent this in a few ways. First of all, we can make some assumptions about the data. One is that we know that the population is normally distributed, so we can assume that because the population is normally distributed, we can assume that the mean of the sample is also normally distributed, and I've represented this in this graph below. The other assumption that we can make is that the mean of this random sample will equal the mean of the population. So the mean, in this case, will equal mu, which equals 1.0875. We can also figure out the standard deviation of the sample population by using a formula which is sigma, or the population standard deviation, divided by the square root of the sample size. We know that the sample size is n equals 8 because we pulled 8 bottles from the pack, which is right there. So now we can actually plug some numbers in, and we can figure out all the things that we need to know in order to determine whether this sample, the mean of this sample, this random sample, will exceed the 1.1 pounds. So one thing I'm going to do is just sort of articulate this in a graph. So here is our mean, which is 1.1 1.0875. And we have a sample size of n. We're not going to put that there, but this x-axis represents the mean, and the y-axis is the weight in pounds. We can also put the 1.1 pounds in here because we know it's probably somewhere out to the right because it's greater than 1.0875. So let's just put it right here. And this is 1.1, and this piece of the curve is what we're actually trying to find out. This little bit right here. One thing I can tell you right off the bat is it's going to be less than a 50% probability. And the reason why I know this is because it's a normal curve, and we know that the center is in the center, and that this particular weight that we're looking for, the probability, is way to the right of center. So I know that it's less than 50%. Kind of a good gauge. So let's figure out what the standard deviation of this chart, of this mean sample is. So I can plug my numbers in, and I'm going to plug in, and I'm just going to, graphically, we're looking at this spread right here to either side. We're looking at this first level standard deviation. So I know that the standard deviation of the population is 0.015, and I know my n is 8, and if I do the calculation here, I should get 0.0053. So now I can figure out that this here is 0.0053 more than 1.0875. If I just add that number to each side, I should get the spread here. So by doing this calculation, I should get something like 1.0928 to the right, and to the left I should get 1.0822. So by doing that calculation, I know now that 1.1 is actually further out than one standard deviation from the mean. So now I need to figure out, well, what's the z-score? Because as you recall, the question specifically asked for the probability that the mean of the random sample exceeds 1.1. So to determine I need to determine the z-score of this value. So I will compute the z-score, and recall that the z-score is equal to x minus mu over sigma. Now in our case, this is a standard z-score here that we have the formula written for, but in our case we're looking at a random sample of the mean of a random sample. So for our case, we need to look at, in this specific case, we need to look at x bar, not x. Recall that x typically resides on the x-axis. In our case, the x-axis is actually x bar because it's a sample of 8 bottles, and it's the mean of the means, essentially. So we have our x bar, mu remains the same, but now the standard deviation is exactly as we calculated above, which is the population standard deviation divided by the square root of the number of samples, of the sample size. If we do some math here, or actually I'll just plug in some of these numbers, so x bar in our case is going to be 1.1, because that's the target number that we're looking for right here. So the 1.1 is x bar. We know mu is 1.0875, and we're dividing that by the population standard deviation, 0.015, divided by the square root of 8, which we've already calculated up here. So if we run through this calculation in its entirety, we should get 2.36 as our final number. So 2.36 is our z-score. So the next step that we need to do is actually look this up on the z-score table. And the number you should find this to be is 0.9909. Now this 99.09 is actually the probability of it being less than. So we're looking at this probability here when we're looking at the 0.9909. What we need to do is we actually need to look at this piece right here. So to do that, we know that the total of all of the probabilities under this curve are going to be 1. The total is going to be 1 if we add everything up. So we know if the total is 1, and we know that the side to the left is 0.9909, then 1 minus that should give us this little piece right here. So if I say 1 minus 0.9909, if I do the math on this, I should get 0.0091. Now, one way to represent some of these things, the 0.9909, we can actually call this the probability of x bar being greater than 2.36. That's our z-score. The second part here we can represent as 1 minus the probability of x bar being greater than 2.36. Just some notation facts. So our answer is that there is a 0.9% chance that the mean of the random sample of 8 bottles that we pull is going to exceed. So the mean of the random sample will exceed 1.1 pounds. And that is your answer.